All right, so this talk is about tridiagonal pairs and UQ-SL2 hat. So I'm going to be discussing this linear algebraic object called a tridiagonal pair. Roughly speaking, this is a pair of diagonalizable linear maps on a finite dimensional vector space that each act on the eigenspaces of the other one in a block tridiagonal fashion. I'll describe the basic features of a tridiagonal pair, including the shape vector, the tridiagonal relations, and the tetrahedron diagram. And then we'll use a tridiagonal pair to construct two modules for the quantum affine algebra UQ-SL2 hat. This talk is based on joint work with Tatsuro and Kenichiro Tanabe. So let me start by defining a tridiagonal pair. Let F be a field, and let V denote a vector space over F with finite positive dimension. And let NV be the F algebra consisting of the F linear maps from V to V. And consider an ordered pair, AA star, of maps in NV. And that pair AA star is called a tridiagonal pair, or TD pair. Okay, whenever each of A and A star is diagonalizable, exists an ordering VI, I0 to D, of the eigenspaces of A, such that for I0 to D, A star applied to VI is contained in the sum of VI minus 1, VI, and VI plus 1. Exists an ordering VI star, I0 to delta, of the eigenspaces of A star, such that for I0 to delta, A applied to VI star is in the sum of VI minus 1 star, VI star, and VI plus 1 star. And finally, there does not exist a subspace W of V that's invariant under the A and the A star, and not equal to 0 and not equal to V. In other words, V is irreducible as a module for the A and A star. Now, according to a common notational convention, A star denotes the conjugate transpose of A. We're not using that convention. In a TD pair, the elements A and A star are arbitrary, subject to the four conditions. The TD pairs were introduced around 1999 by Ito, Tanabe, and myself. Question?
Are those eigenspaces one-dimensional?
I don't know at all if you understood the question.
I didn't quite hear it. Could you repeat that?
Yeah.
Are those eigenspaces assumed to be one-dimensional?
No, they're just,
Thank you.
So the tridiagonal pairs over an algebraically closed field classified up to isomorphism by Ito, Nummer, and myself around 2011. It turns out the TD pairs are related to all kinds of things: Q polynomial distance regular graphs, the orthogonal polynomials of the ASCII scheme, the ASCII-Wilson-Onsager and Q-Onsager algebras, the double affine Heck algebra of type C1 check C1, the Lie algebras SL2 and SL2 hat, and the quantum groups UQ-SL2 and UQ-SL2 hat, and integrable models in statistical mechanics. Now, in our study of tridiagonal pair, it's useful to define a related object called a tridiagonal system. And before defining this object, I'll recall a few concepts. So let AA star denote a TD pair on V. During VI, the eigenspaces of A will be called standard whenever it satisfies that condition 1. A star applied to VI is in the sum of VI minus 1, VI, and VI plus 1. Okay, and if the ordering VI is standard, then the inverted ordering VD minus I is also standard, and no further ordering is standard. Similar comments apply to A star. Also, given an eigenspace W of any diagonalizable linear, the corresponding primitive idempotent acts on W is the identity map, and acts on all other eigenspaces as 0. Now, by a tridiagonal system or TD system on, we mean a sequence phi consisting of an A element, an EI, I0 to D sequence, an A star element, an EI star sequence, I0 to delta, such that AA star is a TD pair on V. The EIs form a standard ordering in the primitive idempotence of A, and the EI stars form a standard ordering in the primitive idempotence for A star. Now, consider a TD system phi. Each of the following is another TD system on V, phi star, in which we interchange the roles of A and A star. Down arrow, in which we leave the A and A star alone, but we invert the ordering on the EI star. Phi double down arrow, in which we leave the A and A star alone, but invert the ordering on the EIs. Now, viewing the star, the down arrow, and the double down arrow, as permutations on the set of all TD system, we see that they satisfy the relations that you see there, the star, the down arrow, double down arrow. Those are involutions. The composition of the double down and the star is equal to the star, and the composition of the star and the down, and so on. The group generated by the three symbols, star, down, double down, subject to the relations that we see there, that's the dihedral group D4. D4 is the group of symmetries of a square and has 8 elements. So the elements star, down, double down induce an action of D4 on the set of all TD system. Two TD systems in the same D4 orbit will be called relatives. So until further notice, let's fix a TD system on phi. Okay, there we have it. For I and j 0 to delta, ei star a ej star is 0 if I and j differ by more than 1, and non-zero if they differ by exactly 1. That's just reflecting this tridiagonal nature of the action of the A on the eigenspaces for the A star. And then we have the dual equation, EI A star EJ is 0 if I and j differ by more than 1, and non-zero if they differ by exactly 1. Okay, these relations, we'll call these the triple product relations. Now for I0D, let theta I be the eigenvalue of A corresponding to EI. For I0 to delta, let theta I star be the eigenvalue of A star corresponding to EI star. So we'll call the sequence theta I0D, the eigenvalue sequence of the TD system. And the theta I star sequence will be called the dual eigenvalue sequence. Okay, now my next general goal is to show that D is equal to delta. So in other words, the number of eigenspaces for the A is equal to the number of eigenspaces for the A star. Now this turns out to be a non-trivial, and I'm going to walk you through the proof in order to motivate what comes next. Okay, anyway, so we start off like so. So for I0 to delta and for J0 to D, let's define a subspace Vij, which is the intersection of two sums. The first sum being E0 star V plus E1 star V up to EI star V. Those EI star V's, that's the ith eigenspace for the A star. Okay, and the second sum, E0 V plus E1 V up to EJV. So for example, setting I equal to delta and J equal to 0, in the first sum, we're going to get E0 star V up to ED star, or delta star V, that's V itself. And in the second sum, we just get E0 V. So, V intersect E0, we just get E0 V. So V delta 0 is just E0 V. And similarly, V0 D is equal to E0 star V. Okay, now if we pick the I and J, small enough, then that intersection might be 0. Let's define capital D to be the minimum value of I plus J such that Vij is not 0. So by construction, the capital D is at most the delta because the V delta 0 was not 0. And also the capital D is at most D because the V0D is not 0. Abbreviate UI for V sub I D minus I for I0 to D. Okay, the A and the A star act nicely on the UIs. A star minus theta I star applied to U is contained in UI minus 1 for I1 to D, and also A star minus theta naught star U naught is equal to 0. And similarly, A minus theta D minus I times the identity sends UI into UI plus 1 for I0 to D minus 1, and A minus theta naught sends UD to 0. First line comes from the fact that A star minus theta I star, how does that act on that first sum of the intersection that gives us the UI, the VID minus I? Well, A star minus theta I star kills off the ith term, the EI star V. And what happens to the second sum, E naught V up to ED minus IV? A star, acting in this tridiagonal fashion, it basically adds one more term to the sum. So the I, when the dust clears, UI gets sent into UI minus 1. Okay, now let's look at the sum of the UIs, I0 to capital D. It's non-zero by the definition of that capital D. It's invariant under the A and the A star by the previous slide. But sum has to equal V. It's a module for the A and the A star, but V was irreducible as a module for the A and A star. Okay, now also by construction, that sum is contained in E naught star V plus E1 star V up to E capital D star V. And it's also contained in E naught V plus E1 V up to E capital D V. So you put all those facts together and you find that the capital D has to equal the lowercase d has to equal the delta. Now, my next goal is to show that the sum of the UIs, which we already saw was equal to V, I'm going to show that that sum is actually direct. Why is that? For I1 to D, the intersection E naught star V plus E1 star V up to EI minus 1 star V, the intersection of that with E naught V plus up to ED minus IV, okay, that's 0. Why is that? That's because the intersection, that's just V sub I minus 1, D minus I minus 1 plus D minus I, that's D minus 1, that's less than the capital D minimum, and so the corresponding V intersection is 0. Now, what else? The sum of U naught plus U1 up to UI minus 1 is contained in the first sum, E naught star V up to E naught EI minus 1 star V, just by construction. And also UI is contained in the sum, the second sum, E naught V up to ED minus IV. So the intersection of, on one side, the U naught up to UI minus 1, and on the other side, UI, is contained in that top intersection, which is 0, saying that UI is a 0 intersection with the U naught plus U1 up to UI minus 1 for every I. That's saying that the sum of the UIs is direct. So the sum V equals the sum over I, 0 to D, UI, is a direct sum. Now, the next result shows how the UI subspaces are related to the eigenspaces for the A and the A star. I 0 to D, U naught plus U1 up to UI is equal to E naught star V plus E1 star V up to EI star V. And also, the sum UI plus 1 up to UD is equal to the sum of E naught V plus E1 V up to ED minus IV. Okay, so that sequence UI, we'll call that the phi split decomposition of V. Now, my next general goal is to show that for I0 to D, the subspaces you see there, EIV, EI star V, UI, and also ED minus IV, E star D minus IV, and UD minus I, they all have the same dimension. Okay, and I'll get at that as follows. For I0 D, define a map Fi in NV that acts as the identity on UI and sends Uj to 0 for j not equal to I. So in other words, Fi is the projection from V onto UI. So by linear algebra, Fi times Fj is delta Ij Fi, and the sum of the Fi's is equal to the identity. And then it turns out that for I less than j, Ej star Fi is 0, Fj Ei star is 0, E minus I Fj is 0, and Fid minus j is 0. And pushing things a bit further, for I0 to D, the triple product Fi Ei star Fi is equal to Fi again. Ei star Fi Ei star is equal to Ei star. And also Fi Ed minus I Fi is equal to Fi, and Ei Fd minus I Ei is equal to E. And what that's telling us is that for I0 to D, the linear maps from UI to Ei star V, sending a vector V to Ei star V, and also going the other way, Ei star V going to UI, sending a vector V to FIV. Those maps are bijections, and moreover, they're inverses. And similarly, the linear maps from UI to ED minus IV, taking a vector V to ED minus IV and going backwards, ED minus IV to UI, sending a vector V to FIV. Those also are bijections and moreover, inverses. Okay, now for I0 D, define rho I to be the dimension of UI. From the bijections on the previous slide, we immediately get that the following subspaces all have dimension rho I. EIV, ED minus IV, EI star V, and E star D minus IV. And moreover, just by construction, rho I is equal to rho D minus I. So that sequence rho I, we'll call that the shape vector. We already showed that the shape vector rho I is symmetric. Rho I is equal to rho D minus I for I0 to D. My next goal is to show that that shape vector is unimodal. Rho I minus 1 is at most rho I for I1 to D over. Get at that by bringing in two more maps, L and R. This is A star minus the sum over I0 to D theta I star Fi And R is A minus the sum of I 0 to D theta D minus I Fi. Okay, now earlier we saw how the A and the A star acted on the UI subspaces. And keeping in mind those Fi's were projections onto the UIs, we find that for I 0 to D, the following hold on UI, L is just A star minus theta I star times the identity. And R is A minus theta D minus I times the identity. So the upshot is that L sends UI into UI minus 1 for I1 to D and sends U0 to 0. And R sends UI into UI plus 1 for I 0 to D minus 1 and sends UD to 0. So we'll call L the lowering map for phi, and we'll call R the raising map for phi. This is all with respect to this split decomposition, the UI sequence. Okay, now it turns out that the following hold for 0 less than or equal to I, less than or equal to J, less than or equal to D. The map R to the power J minus I from UI to UJ is an injection if I plus J is at most D, ijection if I plus J equals D, and a surjection if I plus J is at least D. And similarly, the map L to the power J minus I, UJ to UI, is an injection if I plus J is at least D, a bijection if I plus J is equal to D, and a surjection if I plus J is at most D. However, cautionary note, the maps R to the J minus I and L to the J minus I, these are not inverses in general, even in the case when I plus J is equal to D. Okay, anyway, because of the injectivity discussion in the previous slide, that shape vector, the rho I, satisfy rho I minus 1 is at most rho I for I1 to D over T. Okay, now my next goal is to show that the TD pair AA star satisfies a pair of cubic polynomial equations called the tridiagonal relations. Now, first, I'll assemble a few preliminary results. Let M be the subalgebra of NV generated by the A, being M as a vector space for the moment. It's got a basis consisting of the powers of A to the I 0 to D, and another basis consisting of the primitive idempotency, the EIs, I 0 to D. Now let's consider some elements in M, A star, M. So for I 0 to D minus 1, EI, A star, EI plus 1, minus EI plus 1, A star, EI, can be expressed as a sum E0 plus E1 up to EI times A star minus A star times the same sum. Okay, and pushing things further, for any elements X and Y in M, I didn't say that right. The span of all the elements X A star Y minus Y A star X, where X and Y range over all the elements in M, is equal to the set of elements Z A star minus A star Z, where Z ranges over all the elements in M. Okay, the essential reason for this, behind this lemma, is that those triple product relations, the EI, A star, EJ, they're almost all 0. So you have a huge amount of collapsing amongst the, there's many linear dependencies amongst the terms X, A star, Y, where X and Y are in M. Okay, so now we're ready to state the tridiagonal relations. It's a theorem of Ito, Tanabe, and myself, that there exists a sequence of scalars, beta, gamma, gamma star, rho, rho star, such that the two equations that you see there hold, that bracket is a commutator. We're saying 0 is equal to the commutator of A and the expression A squared A star minus beta A star A plus A star A squared minus gamma A star plus A star A minus rho A star. Okay, and then the next equation is just like it with the A and the A star interchanged. Okay, those two relations, those are the tridiagonal relations that hold, as I'm saying, for any tridiagonal pair, any TD pair. Let me give you a very brief sketch of the proof. It's really not that complicated. Let's assume that the diameter of the D is at least 3, otherwise it's pretty routine. Now, by the previous lemma, taking X to be A squared and Y to be A, there's an element Z in M such that A squared A star A minus A star A squared is equal to Z A star minus A star Z. Now, Z being in M, and M generated by A tells us there's a polynomial f of X with degree at most D, such that Z is equal to f of A. Now, let's take that the preceding equation, line 2, and let it act on the subspaces in the split decomposition, those UIs. if you compare the actions of the two sides, you quickly see that the degree of f of x has to equal 3. And so line 2 becomes the displayed line in the middle there, a squared a star a minus a star a squared, is a linear combination of the commutator of a and a star, the commutator of a squared and a star, and the commutator of a cubed and a star. Okay, and then if we make a mild change of variables, replacing and defining beta to be the alpha 3 coefficient inverse, take away 1, gamma, as you see there, we immediately get the first tridiagonal relation. Okay, and then interchanging the roles of a and a star, we get the second tridiagonal relation. Okay, now those tridiagonal relations can be adjusted by applying an affine transformation to a and a star. I just mean sending a to some linear combination of a and the identity, and sending a star also to a linear combination of a star and the identity. Okay, now over the next few slides, I'm going to display 3 special cases of the tridiagonal relations that may be of interest to you. First example, let beta be 2 and let the gamma gamma star be 0 and the rho and rho star to be 4. In that case, the tridiagonal relations become the Dolan-Grady relations. Triple commutator a star is equal to 4 times the commutator of a and a star, and the same with a and a star interchange. So those Dolan-Grady relations, those are the defining relations for the Onsager-Lie algebra. Next example, suppose beta is q squared plus q to the minus 2. The gamma gamma star is 0 and the rho and rho star are also 0. Then the tridiagonal relations become the q-Serre relations. I'm bringing in a q commutator, a star of type q, q inverse, and plane is equal to 0. And the same with a and a star interchanged. Serre relations, those are the defining relations for the positive part, UQ plus of the quantum group, UQ sl2 hat. Last example, let beta be q squared plus q to the minus 2. The gamma star is 0 and rho star are minus q squared minus q to the minus 2 squared, to pick a normalization. Then the tridiagonal relations become the q Dolan-Grady relations, as you see there. Left-hand side is just like for the q-Serre relations. And then on the right-hand side, instead of 0, we see a scalar multiple of a commutator. So those q Dolan-Grady relations are the defining relations for the Q-Onsager algebra, OQ. Okay, now let's return our attention to the tridiagonal relations in the general. An analysis of those relations reveals that the eigenvalue sequence, the theta i's, and the dual eigenvalue sequence, the theta I stars, each satisfy a 3-term recurrence. Now I'll get to the details on the next slide. It goes like this. So given the scalars, the beta, gamma, gamma star, rho star that satisfy the tridiagonal relations, then each of those ratios you see there, the theta I minus 2 minus theta I plus 1 divided by theta I minus 1 minus theta I, okay, and the starred version, those are all equal to beta plus 1 for I2 to D minus 1. So gamma is equal to theta I minus 1 minus beta theta I plus theta I plus 1 for I1 to D minus 1 and the starred version. And then the rho is equal to theta I minus 1 squared minus beta theta I minus 1 theta I plus theta I squared minus gamma theta I minus 1 plus theta I for I1 to D and the starred version. So we can read off recurrences controlling the theta i's, theta I stars from the beta, gamma, gamma star, and so. Okay, now let's come back to our TD system on V. Phi, there it is. My next general goal is to describe the tetrahedron diagram of Phi. Let me sharpen my notation. By a decomposition of V of length D, I mean a sequence Wi, I0 to D, of non-zero subspaces whose direct sum is equal to V. For example, each of the following form a decomposition of V. The eigenspaces EIV of A, eigenspaces EI star V of A star, and the subspaces, the UI in the phi split decomposition. Let Wi, I0 to D, denote a decomposition of V. I'm going to describe this decomposition by a diagram, as you see there, consisting of a long line segment with dots along it. The dots represent the the WI, the subspaces in the decomposition. Those labels, the WI, might be suppressed as we go along if they're clear from the content. Let's consider two decompositions, WI I0 to D and WI prime I0 to D. We'll be interested in the situation where for I0 to D, the sum W0 plus W1 up to WI is equal to the sum of W0 prime plus W1 prime up to WI prime. And that situation will be described by the diagram you see there, where the two line segments representing the decomposition, the W decomposition, the W prime decomposition, they come together and meet at the W0 equals W0 prime dot. Okay, now we're calling our phi split decomposition UI. So earlier we showed that for I0 to D, U0 plus U1 up to UI is equal to E0 star V up to EI star V. And also UI up to UD is equal to E0 V up to ED minus I. So the corresponding diagram is shown on the next slide. It looks like this. So the U0, U1, U2 sort of sequence comes into the E0 star V, E1 star V sequence, reflecting the first sum on the previous slide. And also the UD minus 1, UD minus 2 sequence comes into the E0 V, E1 V, E2 sequence because of the second equation on the previous slide. Okay, now referring to the phi split decomposition of V, we can replace phi by any relative and get additional decompositions of V. These decompositions are shown on the next slide. So, things, basically we filled in all possible split decompositions up to taking of inverses. There are 4 of them. The two horizontal line segments represent the eigenspace decompositions for the A on the bottom and the A star on the top. Okay, and then the 4 diagonals, so to speak, represent the various split decompositions. Okay, anyway, this diagram, I'll call that the tetrahedron diagram of phi. Okay, so like I said, in the tetrahedron diagram, the horizontal decompositions are the eigenspace decompositions for the A and the A star. Now, it's tempting to view the other 4 decompositions as eigenspace decompositions for some of their maps. And to make progress in this direction, I'm going to impose a mild assumption on the TD system. So for the rest of this talk, let me fix a non-zero Q that's not a root of unity and recall the brackets and Q notation. So our TD system phi will be called Q geometric whenever theta I is q to the power 2i minus d, and theta I star is q to the d minus 2i for I0 to d. Okay, so they're both, the eigenvalue sequence and dual eigenvalue sequence are both in q squared geometric progression. So for the rest of the talk, I'm going to assume that phi has this q geometric type. And in this case, the beta is q squared plus q to the minus 2. Gamma and gamma star are both 0. Rho and rho star are both 0. So those tridiagonal relations become the q-Serre relations. Okay, there they are at the bottom. Now let me bring in a little more notation. Let Wi, I0 to D, be a decomposition of V. When I speak of the corresponding map, I mean the element M and NV such that Wi is an eigenspace for M with eigenvalue d q to the d minus 2i. So M minus q to the d minus 2i times the identity sends Wi to 0 for I0 to D. For a decomposition Wi, the following maps are inverses. The map corresponding to the Wi and the map corresponding to the inverted sequence WD minus I. Now, given a decomposition Wi of V, the corresponding map M will be described by the diagram you see there. We take the line segment that represents the original decomposition, and I'm putting an orientation on it, a little arrow pointing to the right, labeled M, okay, to indicate that M is the map corresponding to that orientation of the line segment. Okay, now I might suppress the labels Wi along with the dots themselves if they're clear from the context. Okay, so for example, going back to the tetrahedron diagram, remember the top and bottom horizontal decompositions were the eigenspace decompositions for the A and the A star. And the eigenvalues for A in that q-squared geometric progression were such that A becomes the map corresponding to that bottom, the decomposition, as long as we put the orientation going to the left. Okay, and A star is the map corresponding to the top decomposition with the orientation going to the right. Now let's define some additional linear maps, B, B star, K, and K star. According to that diagram, let's take B for example. So I'm defining B to be the map corresponding to the decomposition, the vertical decomposition going from the bottom left to the top left in the diagram. Okay, so for example, the imaginary dot at the top left represents the eigenspace for B with eigenvalue q to the minus d, and the imaginary dot at the bottom left corresponds to the eigenspace for B with eigenvalue q to the d. Okay, and so forth. So we got K, K star, and B star maps corresponding to the other various split decompositions. Okay, now the amazing thing is that the A star, B star, K star satisfy many beautiful relations. So over the next few slides, I'm going to show you those relations. So here are the first four. QAB minus Q inverse BA. So in other words, the Q commutator of A and B divided by Q minus Q inverse is equal to the identity. And then something similar involving B and A star, and then A star, B star, and B star A. And then some relations involving the K's, Q commutator of K inverse and A divided by Q minus Q inverse is the identity. And something similar involving B and K inverse, and then K and A star, and then B star and K. And then relations involving the K star, Q commutator of A and K star divided by Q minus Q inverse is equal to the identity. And similar for K star inverse B, A star, K star inverse, and K star B star. Okay, and also it turns out that the B star pair satisfies the q-Serre relations. Okay, now I just gave many relations involving the A star, B star, K star. And I can summarize these relations using the following diagram. Okay, so we see a tetrahedron with various orientations on the edges. And we can read off from this picture the relations on the previous slides according to the following key. For any two arcs with the same endpoints and pointing in the opposite direction, the corresponding maps are inverses. Also, for any two arcs that create a directed path of length 2, the corresponding maps, call them R and S for the moment, satisfy that QI relation, QRS minus Q inverse SR over Q minus Q inverse is equal to the identity. Okay, and then thirdly, for any two arcs that are distinct and parallel, so either horizontal or vertical, the corresponding maps satisfy the q-Serre relations. Okay, now let's bring in UQSL2 hat. Let me remind you how that goes. So define the algebra UQSL2 hat by generators EI plus or minus KI inverse, I is 0 or 1 here. Okay, and the relations you see there, KI inverse really are inverses, K naught, K1, K1, K naught. KI, EI plus or minus KI inverse is Q squared or Q to the minus 2, EI plus minus. Okay, and similar. And then we see at the bottom the q-Serre relations. Okay, those EI plus minus and the KI inverse, those are the Chevrolet generators for UQSL2 hat. Okay, now it's more convenient for us to work with a different presentation, the so-called equitable presentation. This was introduced by Ito and myself around 2003. It goes like this. So it turns out the algebra UQSL2 hat is isomorphic to the algebra with generators yi plus yi minus, ki, ki inverse, I still 0 or 1. Okay, and the relations you see there, the ki are playing the same role as before. Ki inverse, really our inverses. K0, K1 is central. The yi plus against the ki satisfies this qy relation. So does the ki against the yi minus against the yi plus. The yi plus against the yj minus, I not equal to j. They satisfy almost the qy relation, except the right-hand side, the 1 is replaced by the inverse of the product K0, K1. Okay, and then the yi satisfy the q-Serre relations. Okay, anyway, we'll call these yi's and the ki's the equitable generators for UQSL2 hat. Okay, now back to TD systems. So referring to our TD system phi on V of Q geometric type, the vector space V becomes an irreducible UQSL2 module on which the equitable generators act as follows. The y0 plus acts as the B star, the y1 plus acts as the B, the y0 minus acts as the A star, the y1 minus acts as the A, the k0 acts as the capital K, the k1 acts as the K inverse, the k0 inverse acts as the capital K inverse, and the k1 inverse acts as the K. Okay, so basically what I'm telling you is that all those QY relations and q-Serre relations that we saw involving the B's and A's and K's are basically telling us that we're looking at a representation of the UQSL2 hat. Okay, now there's actually two ways to match things up with the UQSL2 hat. According to this second part of the theorem, V becomes an irreducible UQSL2 module on which the equitable generators act in the following way. The y0 plus acts as the A now. The y1 plus acts as the A star. The y0 minus acts as the B star. The y1 minus acts as the B. The k0 acts as the K star, and so forth. So basically, in terms of the tetrahedron diagram, what we're doing is taking the situation with the diagram corresponding to the first table in this slide, and then we're just rotating it 90 degrees to get the situation described in the second table of this slide. Okay, anyway, so given a tridiagonal pair of Q geometric type, in this very natural way, we end up with two irreducible modules for the quantum affine algebra UQSL2 hat. Okay, thank you for your attention.
Thank you, Paul. Are there any questions?
Is there a way to relate the UQSL2 hat irreducible module that you find in this theorem to the, say, other usual classifications of irreducible UQSL2 hat modules?
So the UQSL2 hat modules that come up in this construction, it's almost correct to say that we get up to isomorphism every finite dimensional irreducible UQSL2 hat module. It's not quite true. There is a so-called Drinfeld polynomial attached to any given finite dimensional irreducible UQSL2 hat module, a polynomial in one variable. If you normalize things properly, all the let me say it correctly. Yeah, so the polynomial is constructed from the module as long as that polynomial is not 0 at the argument 1. P of 1 is not equal to 0. So any such module coming from a tridiagonal pair of this key geometric type. Let me remind everybody, so according to the Acharian-Presley classification of the finite dimensional irreducible UQSL2 hat modules, every such module is a tensor product of evaluation modules. It's slightly complicated, but in the end, we have a precise classification of all these finite dimensional modules. Every such module corresponds to a certain Drinfeld polynomial. Okay, and the polynomial, the ones for which the polynomial does not vanish at this argument 1 are precisely the modules for which there's an attached tridiagonal system.
Is there anything that plays the role of the theorem in the case of an indecomposable module when Q is the root of unity?
And when Q is a root of unity? That's a good question. How should I say? That is prime territory for exploration. Somebody other than me. I tend to stick to the Q not of unity case because that's the simplest case. That's the case I can handle, so to speak.
That's another question from the back.
Do you know if there exist tridiagonal pairs for any degeneracy which satisfies you strength rho 1, rho 2 smaller than rho 2, smaller than rho 3? If I choose 1, 7, and 9, do you can construct a tridiagonal pair?
The 1, 7, 9. I'm sorry. Those were the dimensions of the eigenspaces. Yeah. Oh, okay. That's a good question. The theory is not entirely worked out, but there are some. We think we know what happens. So the bottom line is it's not the case that any sequence of dimensions subject to the inequalities that I showed you so far. Not the case that any such sequence can be realized from a tridiagonal system. If you push more deeply into it, you find that if we define a generating function for the dimensions, a so-called shape polynomial. We have the shape sequence rho naught, rho 1 up to rho d. Corresponding generating function in a variable t, let's say, is rho naught plus rho 1 t plus rho 2 t squared, etc., up to rho d t to the d. Okay, so that shape polynomial, if it comes from an actual TD system, conjecturally factors into polynomials of the following sort. So polynomials that correspond to shape polynomials, all the row i's are 1. So 1 plus t squared up to some t to the r. Okay, I'll just for the moment, I'll just call that a good polynomial. Back to the general case, a shape polynomial is realizable by a tridiagonal pair exactly when it is a product of good polynomials. That implies a mild restriction on the possible shape vectors that you could come up with. And I should mention that product or that factorization of the shape polynomial into the product of these good polynomials is a consequence. It kind of reflects the Achari-Presley tensor product decomposition of the underlying UQSL2 hat module into a tensor product of evaluation modules. So somehow each factor in the tensor product decomposition is giving you or corresponds to one of these good polynomials.
Thank you again, Paul. If there's no more question, we'll thank you again. Some advertisements. So Maud de Vichère and Gossterer sent us the notes for in the case of Maud for her mini course last week, and for Gossterer for his Scheherazade that starts tomorrow. They're available from the schedule. So you look at when they spoke and there's a tie to their notes. Professor Lehrer was not able to come. We have the lectures recorded, so we're going to project one every day on Tuesday, Wednesday, Thursday, and Tuesday after, and we'll gather the questions. There's 2 discussion rooms in CRM, one on the 5th floor, one on the 4th floor. They're open for discussion. You just go there and do whatever you want to exchange as information. And we'll resume tomorrow. And tomorrow there's also wine and cheese at, on the schedule, so I don't recall exactly, 5 o'clock. So keep that in mind. Yes, Kavi?
The recorded course will be presented here. The recorded.
Yeah, the presentation will show there, and we'll find a way to send the questions to Professor Lera one way or another. Thank you. Have a good afternoon.